how I did it on my paper. You don't have to do it the same way at all, but just organizationally. I did area all on one side and volume all on one side, and I just was able to work down the paper like that. You guys can do it top and bottom if you want, whatever you want, but there was enough to kind of fill up the paper if I wrote this size, just so that you're aware, the people that are like need to know what's going to happen organizationally, okay? All right, so for area, how do we normally calculate area of, let's say, like a rectangular shaped object? What is our formula for area for something like that? Yeah, length times width, right? So our area is just equal to length times width, okay? So the first thing we're going to do is say, let's say that you knew the side lengths. Okay, let's say it was a square, just to make our calculations a little bit easier, so that means our length and our width are the same. And let's say that the square was 3 by 3. So the area then of my square would be what? 9, okay? Then let's say, like we were talking about with the piece of paper, let's say I want to double all of the side lengths, okay? So I'm basically going to talk about a new square that's larger, okay? And I want to double the side lengths, okay? Which means instead of this side length being equal to 3, what's it going to be equal to? 6. Okay, so I'm going to write 6, but I also am going to write 3 times 2 because I want to try and show you guys where some of the math is coming from, and you might see it better if we use 3 times 2 instead of just writing 6, okay? And this side's going to be the same, 6, but we're going to think of it as 3 times 2. But since we have numbers, look at what happened to the area for a minute. You just doubled the length and doubled the width. Did you double the area? No. What's the new area of this square? 36. So the side lengths got doubled, but what happened to the area? It didn't get multiplied by 2. What did it get multiplied by? 4. Okay? Does anybody have any idea why that's happening? Why, if the side lengths got multiplied by 2, would the area end up being multiplied by 4? Yes, sir. Good, because it's squared. So when we're calculating area of a two-dimensional object, how many dimensions are we using in our area calculation? It's two-dimensional, 2, right? So what's really happening here is here we did area length times width. To get the answer, we did 3 times 3. Okay? Here, when we go to calculate the area, if we think about it as length times width, think about what the length is. I know 6 is what we wrote, but remember how we got 6. We did 3 times 2, right? And the width, we had the same thing. Can you multiply numbers in any order that you want? Right? So I don't have to do 3 times 2 times 3 times 2. I can kind of group them however I want, right, because of the commutative property of multiplication. So I'm going to rewrite this a different way just so that you can see what happened. We have 2 3s multiplying each other. That's just like what we had before. But we have now an extra 2 in the multiplication and another extra 2 because we had 2 side lengths and they were both doubled. So we have that times 2 showing up twice. So basically, we're getting our original area that we had, and it's being multiplied by whatever you're increasing the side length by, but squared because there's 2 side lengths. Okay? Is that okay with everybody? Right? General idea. Okay, so the reason I'm pointing it out that way is because it's a little bit harder when we think about going backwards. And we'll put a little formula here just so that you guys can kind of see what happened. Oops. All right, so our formula here basically is saying that our new area is equal to this part, which was our old area calculation, right, that we had done before we expanded it. So it's equal to the old area times, and in this case it was 2 squared. We talked about the squared being because there's 2 dimensions, 2 different side lengths that we're increasing. Why was this number 2? So this 2 is because it's happening twice, here and here. Why was this number a 2? What about the problem made this be a 2? Yeah, we said we were going to double the sides, so this was a 2. Which means if I had said I was going to triple the sides, what number would this be? 3. Okay, if I was going to quadruple them, it would be a 4. So basically, the number that's right here is whatever you're multiplying the side lengths by, and then it's going to be squared every time you're dealing with area, because area only has 2 dimensions. Is that okay with everybody? So it's kind of a vague formula, like, oh, if I'm expanding something, I can get my new area by just taking the old area and saying I'm multiplying the sides by this, but square it because there's 2 sides. So what if somebody asks it the other way? What if they tell you how much the area has changed, but you're supposed to figure out then what they multiplied by the side lengths, which makes it a little more difficult because you don't have all the numbers to just do the straightforward calculation. Okay? So let's say that we start with the square length of 9 again, and we say we want to triple the area. This is like a new problem, but still about area, okay? I know, my word space is weird. I want to keep that one up there, though, so we can refer to it. All right, so we're still going to start with this same square with an area of 9, and that means we know that it's 3 by 3 because that's the area, okay? But what I'm telling you this time is instead of telling you, I want you to multiply each side by 2, which then meant you need the side lengths, and you could take the side lengths and find the area. I'm going to give you a little less information, and I'm just going to say I want you to triple the area. So think about what that means. So you actually know the new area. What would the new area be if we're tripling the original area? 27. So the original area was 9. 27. So we've tripled it, or it's had 200% growth, right? Because 18, but grow it on top of the 9 you already had would give you the 27, okay? But then the question is, what happened to the side lengths? What happened to each of the 3s? What did they get multiplied by? Now, if we're assuming they both got multiplied by something, we're assuming it grew proportionally. In your projects, you guys have looked at your stuff. Is all of it growing proportionally? Not necessarily. So can you do the calculations if it would have grown proportionally? Yes. But in your reflection and some things like that, there's even a specific question about it. If it grew proportionally, that's where you would discuss, like, oh, this might be a little bit off because this part of it didn't grow as much as this part of it, okay? Which is also why you measured, like, appendages and things like that, okay? All right, so we know the area. So again, think about how we got the area calculation. Over here, we're doing length times width, right? And then there's some mystery number that our sides were multiplied by to make this new area of 27. So when I think about these, I'm thinking about this being the 3 that it was before multiplied by some mystery number that represents some sort of growth for this. Okay? And then the same thing is happening to this side of the square. So over here, area is still going to be length times width, but remember what we did right here, right? Our length here is 3 being multiplied by some random x number that we don't know and we're trying to figure out, and our width is the same thing. And we said that we could rearrange those, right? The original area calculation together, and then all the extra things that are now multiplying in. Okay? So notice that this looks a lot like this. Okay? So this is where we got our formula from. The new area, which we have as 27, is equal to the old area, which was originally 9, and we can see that by our 3 times 3, multiplied by whatever you multiplied the side lengths by squared because it has 2 dimensions. So I didn't have to draw all of this. I could have skipped right here if I have good understanding of this formula and why it's happening, right? How do you solve an equation that looks like this? 27 equals 9 times x squared. Isolate the x. Okay, so x is being multiplied by 9, so we're going to divide by 9. Does anybody have any idea why this ended up being 3? What did I say in the problem? We were tripling the area. So, of course, if I take the new area and divide it by the old area, I'm going to get 3, because I specifically said in the problem I was tripling it, right? So that kind of gives you, if you get that, you can kind of get to a quicker place without having to plug in the exact numbers every time. All right, so we get x squared equals 3. What do you do at this point to solve this equation? Square root. Okay. And technically, when you square root both sides of an equation, what do you have to remember when you're solving it? Plus or minus, okay? But in this case, do we include both the plus and the minus? No, because we're talking about a geometric figure, right, where the length of the sides actually exists. So could it be negative 3 times something? No. Okay, so we're only going to use the positive in this case, not because I'm changing the rules of algebra and how it works, but because we have a context, and this is a measurement, and our measurement would be positive. Does that make sense to everybody? So our x value is rad 3. What have I just figured out with rad 3? What does rad 3 represent? What were we trying to find? Not just the sides. It has something to do with the sides, so that's right. But what value is it? The side length is not actually rad 3. What is the new side length? It's what they were multiplied by. So basically, if you took the original side lengths and you multiplied them by square root of 3, you would get this new triple area. Okay? Thank you. All right, so what if I didn't want to triple the area? What if I wanted the area to be 5 times larger? What do you guys think would happen? Think about it. So your area, your new area is equal to your area times whatever the sides were multiplied by squared. Okay? So I didn't tell you a number this time. You have some old area. I don't care what it is. Just call it A for a minute. Okay? If I want your new area to be 5 times larger, what can I write right here if I'm calling the old area A? What is the new area? 5A, right? 5 times bigger than A. Okay? What's going to happen to those A's every time in this equation? How can I go about solving this? If I'm trying to look for X, I don't want A in there. Okay? So when we go to isolate X, if we divide by A, those A's cancel, right? You might not think that's very nice, but look what happens on the other side. When you divide by A, the A's cancel. That's going to happen every time, right? Because every time I say, I want you to make the new area 12 times bigger, 18 times bigger, you're always going to have an A and a something times A. So the A's are always going to cancel. And so you're going to be left with the stuff I'm multiplying the side lengths by squared is equal to 5. Use your square root to get rid of the square. So the side length would be multiplied by rad 5 when I want the area to be 5 times bigger. So what if I wanted the area to be 18 times bigger? What do you think the side lengths are going to get multiplied by? You're right. A little bit louder, people with that. Rad 18. What if I want the area to grow 1 million times larger? What would each side length be multiplied by? Right? Rad 1,000,000. Okay? Why a square root every time? Because we were dealing with 2 dimensions, right? And to solve that, we'd have to take a square root to get rid of the squared. Is this okay with everybody? All right? So you're going to use some of these formulas to help you get through the problems. We'll go through them in a minute. Okay? The problems on there, though, aren't only about area. They're also about volume. What do you think we have to take into consideration additionally if we start talking about volume instead of area? The height. So we add in a 3rd dimension, right? So instead of looking at a sheet of paper, we're looking at a fairy or a shark or a robot, right? Something that has 3 different measurements that you called length, width, and height that would calculate its volume, okay? So this is important in our project, right? Okay, so for volume, I understand your objects are weird shaped, but we can just do length, width, height, and kind of treat it like it's a little box of that length, width, and height, even though we know it has all these things going on, okay? Here, we'll make some nice side lengths for ourselves that aren't too crazy. Okay, so let's say you have this length, width, and height measurement of some 3-dimensional object, and those measurements are 3, 2, and 1, okay? So what is the formula for volume of an object? Length times width times height. So again, almost like area, but third dimension is now multiplying into this, okay? Any predictions about how that's going to affect the math like we just saw for the area? Yeah, stuff is going to look cubed now, right? Because we're dealing with 3 dimensions instead of 2 dimensions, which means one more side multiplying in there, okay? So if you look at what happens, now when you double the sides, and again, I know how to multiply everything by 2, but I'm going to write it out as times 2 because it helps us see what's happening. This 3 is going to be times by 2. The 1 is going to be times by 2. And the 2 is going to be times by 2. So when you go to do the volume calculation in this first prism, our original one, we had a length of 3, a width of 1, a height of 2, okay, for a volume calculation of 6. If we do the new calculation over here, okay, our length is no longer 3. It's 3 getting multiplied by a 2. Okay. Again, I know that that's 6, but again, I'm trying to show you guys how to do it when it gets a little tougher with variables, so I'm keeping the numbers a little bit separated. The width is no longer 1. The width is 1 being multiplied by 2. And the height is no longer 2. It's 2 being multiplied by 2. So you got a lot of things multiplying together, and we already said we can rearrange them in any order that we want. So to allow you guys to see this better, I'm going to think about the original side lengths, 3 times 1 times 2, as one group that's being multiplied. And then what I see left is 2 times 2 times 2. Okay. So I see our original volume of 6 is getting multiplied by 2 to the third power. So it's just like you guys said, okay, about what's going to happen with the volume calculation compared to the area calculation. This third power is here because there's 3 different measurements that we're multiplying together, and that's because when we do a volume calculation, we're calculating in 3 dimensions, okay? Why is this 2 here? Yeah, because I said in the problem that we were going to double the side length, so that would change depending on what you were doing with the sides, right? And this is here because of the original volume calculation. So we kind of get the same kind of similar formula going on here, that the new volume can be calculated by taking your old volume and multiplying it by whatever the number is that each of the sides are getting multiplied by, but this time you have to cube it because you have 3 different ones of those numbers going into your formula and multiplying together. Okay? All right, so just like with the area one, we want to be able to do a harder one where I don't tell you how much the sides increased. Instead, I look at the volume. That's what you guys are going to see in your project, right? You had original measurements that could calculate a volume if you wanted to or if you chose to. Now you're going to have new measurements that can calculate a volume. So you're going to have a beginning volume and an ending volume. And the question is going to be, how much did each dimension change? And then you can see if it actually changed proportionally, right? Did each dimension really change that much by your individual measurements? Okay? So if I tell you that, let's see, our original volume, let's keep what we had before, is 6. So we'll just keep that same little picture that we had with a volume of 6. Okay? And I tell you that we are going to triple the volume. What is the new volume of our object? So original volume was 6. I'm telling you it's going to be tripled, therefore the new volume is 18. Any idea what percent growth that would be as a side note? $200%, right? It's 3 times bigger, but that's really only 200% growth because you had a 6 there already. It grew 12. 12 is 200% of 6, okay? But then when you add that back to the original, you ended up with the number 18. So 3 times bigger is 200% growth or 200% increase from the original size. Does that make sense to everybody? All right, so we tripled the volume, and the question is, what happened to the dimensions? Okay, so remember over here, This volume was made by multiplying your original length, width, and height together. Okay? This volume is made by doing the same thing, but each of those is being multiplied by some mystery number. If it's growing proportionally. And again, I would do all my calculations as if it was, and then in the questions for your project, I would answer the places that I saw disproportionate growth based on the number calculations and visually based on what I could see for my creature. Okay? So this is just like having the original volume calculation, and like we mentioned before, whatever that number is being cubed. Okay? So our new volume we know is 18. This is equivalent to what our old volume was, length times width times height without the extra factorand, which was 6. And then we have x cubed. How am I going to solve that equation? Okay, first divide by 6 to isolate the x. So when we do that, we'll have 3 equals x cubed, okay? Which means that x is equal to what? The cube root of 3 instead of the square root of 3 because of our 3 dimensions causing this 3 here, okay? So if I wanted to triple the volume, I would expect each side to increase or be multiplied by a cube root of 3. I've stretched that way, okay? So what if I wanted the volume to be 5 times larger than the original? Cube root of 5. So, yeah. So if I want the volume to be 5 times the original, remember, we said our new volume is basically equal to our old volume times x to the third because it's happening for each different dimension. Okay? So if I have some old volume, I'm just going to call it v, but I want it to be 5 times larger, 5v. I can figure this out even without knowing the exact volume number, right? Because what's going to happen to each side of the equation with the v? When I cancel it out on one side, it's also going to cancel out on the other side. So I'm going to have 5 equals x cubed, which means each side was being multiplied by the cube root of 5. Okay? If I wanted to multiply the volume times 10, so here was my original object. Here it is new, 10 times more volume than before. What was each side length multiplied by to get that? The cube root of 10. If I wanted the volume to be 1,000,000 times more, okay, so here's my original volume, here's my volume 1,000,000 times more. What was each side length multiplied by to obtain that? The cube root of 1,000,000, okay, because it's the same thing is going to happen every time. You're going to have an original volume and a number times that volume. So the volumes will cancel, and what's left for your side lengths to be multiplied by is always going to be the cube root of whatever you were multiplying your volume by. Okay? So same process as area, but one's with a square and one's with a cube. Okay? When you're doing your project, so you might get your creature out, right? You measured length, width, and height originally. So you could calculate kind of a general, generic volume for your creature. I get it has all different kinds of things going on, okay? But if we thought about it like a little box, length, width, and height. Then you take it out tomorrow. You get new length, width, height measurements, okay? You can see a new volume. If you want to know percent growth for volume, you take your new volume minus your old volume, divided by the original one, the old one, and you get your percent growth, right? That's the percent change in volume. Okay. Then once you see how many more times it grew, so you say, oh, this is the percentage, okay, and according to your numbers, you're like, oh, this is this many times more, you can know how much each length should have grown by just taking the cube root of that. Now, when you go through individually and you compare length to length, width to width, height to height, it might be disproportionate and it might not meet your expectation, but you now have a calculation you can do to decide what the expectation is. Okay? Does that make sense to everybody? When you're doing weight, you're just going to be dealing with one number, so you're not going to need all of this. You just have an old weight and a new weight, and that's one measurement. With girth, you just have one number around, and you have an old girth and a new girth, and that's one measurement. but the volume will be a little more, difficult to deal with because it grows in 3 dimensions, right? So we have to think about with our creature, when the product says it grows up to 600% or it grows 600%, first we have to understand, like, if they really mean 600% growth, okay, how much bigger do they really mean, right? And then to grow 5 times bigger doesn't necessarily mean grow 5 times longer here, 5 times longer here, and 5 times longer there, right? It really means just grow the cube root of 5 times longer here, the cube root of 5 times longer here, and the cube root of 5 times longer here. Okay, so 600% might not be as big as you originally thought, because it doesn't mean that everything's getting multiplied by a large number this way, and this way, and this way. It's getting multiplied by a much smaller number this way, and this way, that together, when they multiply, make that large number that you were thinking of. Okay? So you just have to think about that when you're doing your analysis, your new measurements, and your calculations. Okay? All right.